Okay, so this is AI for social good, right? So in general, we try to make complex, we try to make complicated computer science softwares and all, but it is different than what is complex. Uh, Complex systems are real world systems in which, in any system, if there are components, they might interact in a non-linear fashion. So that makes it a hard problem to model. It's different from complicated. Complicated means it has much sophistications. There is much complicated architecture, wirings and all, but we can always understand it. But in complex, two components interact non-linearly. So unless you are able to figure out what is that non-linear function that maps them, we won't be able to understand the system. So the systems in society or the one I study are complex systems. Like I study about atmosphere, how to model rain, but there are even more complex systems like the Earth system, hydrosphere, cryosphere, and all the spheres. The human body itself is a complex system. So when I say complex, I again mean when two components of the system are interacting, there might be a non-linear mapping between them. And also another thing about complex system is that the working of the system is multi-scale. So if you zoom in into the working of the system, you will discover new physics which governs it. Because as soon as you zoom out, there might be some emerging property which comes out of the system's overall working. So if in a society, if you look at a family, there's a working, but if you look at the whole city, there might be some emergent property. So there might be multiple physics at multiple scales that run. So there is not one scale that can understand all of the system. So that makes it a very challenging problem to understand. But why are we interested? Why are we interested to understand a system? It can be any system. For me, it's atmosphere. For you, it can be a city, a society, a human body for healthcare, anything. But we try to understand it because we would want to predict what will happen, so we can take necessary actions beforehand. And we can intervene in because if we know the mechanics, the governing equations, what governs the system, then we can do it in our favor if we understand how it works, if we understand the mapping between the components of the system. So how do researchers make this? There are many algorithms. Machine learning is one popular one. There are physics governing equations which before the onset of machine learning, it was almost ruling. So you know all of the Newton laws, and all of them are essentially governing equations which are trying to explain you how that particular system works. And there is network science. If you, it's a course at IIT Gandhinagar. That's also another way to understand complex systems. Game theory and many ways. Biomimicry is also there. But today, I think you guys are very well aware of machine learning, and you might have also learned about physics, how physics enables us to understand the system. But today's session is about how can we use best of both worlds, machine learning as well as physics, because there are limitations and advantages in both the process. And if anybody is not following, if you want to ask, you can ask me questions. So just a quick recap. What is machine learning? So machine learning very simply is different than programming because we don't explicitly give programming rules to the model that we are making. We somehow make an algorithm which optimizes itself to find the mapping, find the function which relates to our x and y. So that is machine learning, and I hope you are all very much aware of it. There are three major types: supervised, unsupervised, reinforced, and there's one popular one, neural networks. Neural networks are special because they have something known as activation functions. Activation function essentially enables us to map non-linear relations because they are non-linear in nature, and they have been proved very powerful in the last 5 to 6 years, 10 years maybe. But they have their own limitations, but strengths too. So this is what about machine learning. I hope you are very much aware about this. So what are the major limitations of machine learning? The first is very popular: garbage in, garbage out. So if the signal to noise ratio, what you are trying to actually understand out of the observations, if there is so much noise and signal is very less, then the model will not really learn anything. So that's called garbage in, garbage out. And there are underfitting problems, overfitting problems. like neural networks, the thing about neural networks is it has so many layers and so many nonlinear activation functions that you cannot really interpret anything. You just have good output, you just have good prediction. It's not interpretable, it's not explainable. And also they are very heavy when it comes to train them, because you need lots and lots of data, because they start from zero, they start from random initialization in the whole function space, and we expect the model to understand the system entirely, which requires so much training data. Even if you have much of training data, and even if we don't care about interpretability, there is one issue, a popular issue we face in climate modeling also. It's about generalization. So suppose you observe a system in some time range, and if in that time range there is some distribution of a variable, and we train it on it, it will work very fantastically in that distribution. But let's say things like climate change happen, so the distribution itself changes. So it becomes an out of distribution prediction, which it miserably fails at, because it has been trained on that distribution. Now we are going out of distribution, so it doesn't know how to take care of it. So that's called as generalization issue. Are you following with me? Okay. Now, what are the, like we studied from high school, what are physics, system dynamics, differential equations? This is a good way and is very popular before the rise of machine learning. It was super popular, and it is still. The thing about this is that you observe a system, you identify the components, you look what are the feedback loops. How does one component interact with other component? How is the feedback loop? This goes over here, this goes over there. You identify some relations, that du by dx is equal to alpha times del square u by del square t. Some sort of relation you identify, either just observing so much of examples and taking trial and error. So you list down this differential equations, or what we call physics laws, if it is verified very properly. So we have this laws that comes under physics or system dynamics. Now, this way of understanding a system is used in numerical weather prediction in my field. It can be used in your field likewise. So what we do over here is we distribute Earth into 3D grid. So grid is essentially a mesh. At every mesh, we ask that system should respect the governing law. So a governing law can be a mass should be conserved. If water balance should be there. If water is coming, that same amount of water should go. It should not violate some principles, like momentum should be conserved. Something about physics that we know should be respected. We check it at every mesh, every grid, and then we move ahead in the next time step. Delta t, we go on. So, do you guys understand what is a governing equation? What are boundary conditions? What are initial conditions? Do you guys understand it? So, boundary condition is, if in any system there is a, let's say, a rectangle is our area, then boundary condition is something which is respected on the boundary. So, maybe at all x at any time t u is 5. That's a boundary condition. What is an initial condition? Initial condition is something which just before starting our calculations, we know it. So, u at t equal to 0, for any x we have a function, it is 6x square. So, we know at all x what is u at only t equal to 0. That's an initial condition. And governing equations are the popular governing equations. It can be anything, a differential equation with some parameter, du by dx is equal to alpha times du square by dt square, something of sorts. So I hope you understand both. What does physics, how does physics go ahead with, and how does machine learning goes ahead with? What are the limitations of this thing, physics or system dynamics approach? First is computational complexity. It's very standard. Suppose, because you are respecting this governing equations, it's always better if you have smaller grid size, as small as you can go. You want a 1 kilometer grid size, but we actually work on 100 kilometers. And it increases the computation cost, increases like many folds itself. So that's one big problem, a really big problem. Even for the current NWP models, numerical weather prediction models, it requires many supercomputers just for some predictions ahead. So that's a expensive task. And the thing about physics, you might also wonder, whenever we study what is gravitation, they say 2 point masses in some vacuum and stuff. It's so simplified that it actually doesn't have enough information about how our system works. It takes our system in some hypothetical space and understands just one relationship between them. But you will always know there are many physics which are working, and that relationship is nonlinear because there are many physics which are working. But we simplify it, which is nice, but that's a limitation. Scale limitation, as I said, compute is a problem. So what we do is, if compute is a problem, and if suppose there is this grid, and there is some physics happening in that grid, something is happening. If we cannot actually compute it, what we will do is, we will make a linear equation or parameterize it, what we call. We will basically not compute it always, we will give a direct mapping, which is kind of approximate. So if points are like this, I will just give it a line, which is super cheap, because compute completely reduces. We are not actually computing the governing equation, if you are understanding. So that scale limitation makes it less expensive. Means if you increase the scale, the cost reduces. And also measurement is also an issue. That do you measure your boundary conditions well? Because it's always, because if you, let's say I work on Earth, then are you measuring, are the satellites measurement accurate, initial conditions accurate, are they timely, are they shifted? That kind of problems are also there. So these are the limitations, but both have their strength. Now let's get open to this new idea. Can we possibly embed our prior knowledge, that is the physics that we know about the system, into a machine learning algorithm? And I'm talking specifically about Earth, but you can do this in human body, you can do this on a society, city, any complex system you want. If you have any prior knowledge about the system and you want the machine learning algorithm to know about it, can you do that? Yes, it's possible. So in this diagram, what they show is, scientific computing is what physics-based approach is. Machine learning is what data-based approach is. Data-based approach doesn't care about physics. It just says that give me data, I will do label minus observation, I think observation minus prediction, and I will compute the loss, I will go for the optimization, and I will minimize the loss. All I'm good at is doing good predictions. Sometimes if you go for machine learning algorithm in Earth system, you might get mass as negative, because it doesn't care. All it cares about is the rainfall closer to what it is. It doesn't care about if mass is going negative or not, but it should not happen. But physics is not like that. Physics might compromise with accuracy, but it will not make mass as negative or any kind of violation of some physical laws that we know about the system. So in between, is there a space in between where we can respect this and take advantage of this accuracy factor? So our model, that resulting model, is more reliable due to physics, and also it is more accurate due to machine learning. So first is regularization effect, as I said, and information enhancement. The physics gives some information, and better generalization due to physics again. But how can you do this? You can do this popularly through three methods. Today we are going to learn one of it, which is loss function modification, which is also known as physics informed neural networks in the starters case. Second is architecture design. So if you have read about CNN, you know, how many of you know CNN? What is CNN? So images, there is some translational invariance, right? A cat at this side of the photo and cat at this side of the photo is still a cat only. So we know that as a fact. If we embed it in the architecture like we do in CNN, that's something we are embedding because we had a prior knowledge about the system, that cat is cat. It is here or there, it's still a cat. So you can make architecture such, if you have any invariant in the system, you can embed it into the architecture itself. Data augmentation, if you want to train machine learning algorithms, you need lots and lots of data. If you have X data, you want 2X data, you can augment it. Just use physics so that it's not violated. Because if you just rubbishly multiply your data sets, then it won't make sense. But if you make it, like, let's say cat is there, you don't make cat's ear with the nose and stuff like that. So you keep that and just one cat image over here, one over here, one over here, one over here. So you have 4 images. You augmented the data. You have 4 times now. So that's some ways to know prior knowledge and embed it into ML. So this is what we are going to study. What is the time now? 11:26. What are physics informed neural networks? So do you guys know how a neural network trains? Like you go find a loss function, you optimize it, backprop, iterate. You randomly initialize. You know it, right? So this is very simple. What we do over here is we keep it mostly same. Just that what is our loss function? Earlier our loss function was something on the lines of prediction minus observation, some function of that. Like you can square it, call it MSE and stuff. So that's our loss function. That this is how much it is deviating from our actual observation. In physics inform, what you will do, you will inform the loss function regarding the physics which should be respected. So taking a simple example of heat equation. So heat equation is governed, the governing equation for it is del U by del T is alpha time del square U by del X square. Quite simple. So if you have U at any point, you just put it over here, it should equate. But now suppose you randomly start it. Okay, so please listen to this part. Suppose you randomly start it, randomly take any U, that might not equate. That governing equation might not be respected. There will be a residual which will be there. If it is respected, it is well and good, but mostly it won't, because you will randomly initialize your input vectors. So you find the residual. The residual will be just take it on this hand side and then find the difference. That will be a residual. And you will square it and average it. So that is the physics laws that you want to inform to the machine learning algorithm. So whenever it goes through the forward loop, the loss function will be determined not only by the observation minus prediction square, but we'll also add another physics laws, which is this. And one technical detail, this is how is this enabled. So autodiff is basically, if you start with some input vector x, you go to our label u, then governing equation, how does it look like? It looks like del u by del t, del square u by del x square. So t and x are our input vectors and u is our output vector. So you have to find that differential. So that is enabled via autodiff. You can always do that. That was the enabling factor which gave the possibility of having this physics informed neural network. So everybody understood what is PINN, like what makes it different. Just you add one loss term, okay, and in this you can also add boundary loss. As I explained you what is boundary conditions, what are initial conditions, you can add that term also. Just add it, simple as it is. So what is our total loss function? Our total loss function will be data loss, which is the standard which we use in machine learning algo, physics loss, and boundary loss or initial condition loss. We can add that too. Now I think you are following this part, right? So there is term lambda f and lambda b. So you might want to, so if you see, L physics might be a very big quantity with respect to L data, just by its virtue. So the quantities that they are, it might be in orders of 100 and this might be in orders of 1, 2 like that. So you might want to make them proportionate so that the model, when calculating the loss function, change in every component L data is actually taken up by the model. So those are for adapting it to it. So if L physics is very big, we will do it 1 by 100. So they are in the same range. So we can do, that's adaptive making of it. Okay. So that's pretty much it. There are more details to it. I will talk about it. So what are the advantages of PINN? Whatever we thought of, we could get. So physical consistency, because we are respecting the governing equations. There is data efficiency. So if you know physics of systems, so you're in numerical weather prediction, you actually don't need any data. All you need is initial condition, boundary condition, and governing equations. You can simply move ahead. But in machine learning, you need data. You need data at every time step. You need data at so many points. So here there is, I need so much data, and here it says I need no data, I just need equations. And this in between things, it says I need some equations because they need to make this loops. But because I already know the governing equations, I can do it quickly, because the scope of how the loss function travels towards its minima becomes very narrow, because always the physics has to be respected. So it cannot go anywhere. It has to respect the physics. So very less data will enable us to go towards the minima. You get this? Forward problems, inverse problems. Do you understand what are forward problems, inverse problems? Anybody? No? Okay, so in physics, or in any system, if you have a governing equation, like we had in this heat equation, del U by del X equal to alpha times del square U by del T square, a forward problem is when you want to find what is the alpha. No, forward problem is when you know alpha already and you want to find what is U in terms of X and T. So you know alpha is 3, let's say. So the equation is del U by del X equal to 3 del square U by del T square. And then you want to find what is U. So that's forward problem. What is inverse problem? Inverse problem is when alpha itself is not known. And you want to find what alpha is for this system. So those are known as inverse problems. This is a very simple case. This extrapolates to all sorts of problems wherever you find differential equations. And computational efficiency. So in NWP or physics based, we have seen at every grade you have to solve those equations. But here it's not such. Because in machine learning there is no mesh requirement or such. So there it's mesh free. It's interpretable, obviously, given we have physics into it, and it's flexible. The thing about this thing now, it opens up it can basically solve most of the problems. So if it can solve most of the problems, it's in a bad way. That's a way to see it. Because now we have opened up a method which can solve just about anything. You have some governing equations, some sparse data, and you are actually claiming that you can really understand the system. But that doesn't really work out well. Means it works out, but not mostly in complex systems. So what are the limitations? So this, by the way, this PINN, this came up in 2019. So there have been many improvements, many modifications to the model. Many of its technical problems were solved, optimized. Today we are sticking to the one which came in 2019, the most basic one. These problems in some way have been attended to. So vanishing gradient. So you know the differential equation, right? It was second derivative. Suppose it's a fifth derivative. Till it goes back to the hidden layer to our input, it will be so many gradients that either the gradient will explode or it will vanish. That will make it basically too important or too ignorant. In any case, it's not helping us. So we want it to be balanced. We don't want the gradient to vanish. Second is loss imbalance. So as I explained, we have those lambda b and lambda f, which tries to balance the weight that boundary loss gets, physics loss gets, and data loss gets. But it's not as easy as it seems because we don't know how it will fade out in next time steps. So we need adaptive learning at every time step. Can we make lambda which is helpful in that sense? Stiff equations. This is the problem which is a key problem. So as I said, this physics informed neural network, they basically open up to solve any complex system if we know some data and some governing equations. But then we would have solved everything, but we are not solving it. So why? Because the real thing is the Earth system or something is really complex. So it's not always a convex function. A convex function is easy to optimize because you can go to the minima over here. But it might be a non-convex function. It might be oscillatory. It might be just flat. So where you initialize it, it might hit that not the real minima. So it's hard with that. And there are some more technical optimization instabilities while we go backprop and if our sampling, so what is sampling? If you have sparse data, the co-location points that we are getting out of system, if those systems are not the correct representation of the system that we are studying, that's bad sampling. And that will not, it's like garbage in, garbage out type thing. So that might also affect our model performance. Okay, so do you guys all understand what is PINN? Yeah, I'll take it as yes. Okay, so this is one application of physics informed neural network, neural GCM. So this neural GCM is state of the art machine learning model, which is a weather and climate model that forecasts precipitation and tries to capture extreme events. You guys are following, right? Is it fast or slow? You understanding? Okay, so you know what a GCM is? Anybody? General circulation models, atmospheric models. So there is water cycle, right? Convection happens, cloud becomes, rainfall happens, this cycle. So atmosphere has circulation. Warm air goes up, cold down. There are many circulations that are happening. And GCM, general circulation models, are the models which were traditionally NWPs. They were numerical weather predictions. That is, they at every grid they calculated the governing equation, boundary conditions, initial condition, and moved ahead. So those are GCMs. Those enable us to understand the atmosphere and enable us to predict with certain accuracy. Let's say 15-day lead time. A lead time is how many days ahead you predict about the system. Neural comes from the word neural network. So there is a machine learning component in this. But now why are we studying it? We are studying it because there are many intricacies in this model, but the primary one we are interested in is how they design the loss function. So the loss function that they designed was L data, which is the standard neural network loss, but they also included L physics, which is the water balance equations in any grid. So P precipitation, so water cycle, it will not disappear, right? It will be still water in some way or other, it will be water, so it should be conserved. So precipitation, evaporation, and all this are meteorological scientists have came up with this governing equation for water balance. So this should be governed, this should not be violated. So we are aware of this. We want this knowledge to embed in our machine learning algorithms. Now, why do we do that? If supercomputers are already there, we have so much of compute available, so much of knowledge, so much like 50,000, more than 50,000 paper exists just on the keyword monsoon. So if we have so much knowledge, then why do we need it? There are many reasons. One is signal to noise ratios. We have so much data, petabytes of data, but there's lots of noise in it. And we might not want to handle always the petabyte of data. So we want to make use of sparse data and still understand the system. It's same with your systems also. Human body also has many sensors, much of data, but we want to make optimized use of data. So that's why they came up with this to use data whatever is available from 1970s, early data, and they put this governing equation in the loss function, and then they started optimizing it. So this is neural GCM. I will explain with a little more detail to you. So if you know stuff, I hope you understand some things. So Earth, that many Earth pictures are the states of Earth. So you have Earth at t equal to 0, t equal to 1, 2, 3, 4, so on. Forcing, what is forcing? Whatever is our system, if anything out of the system is interfering with the system, is forcing. Like in our case, it's solar insolation, it's a volcano, or it's pollution by humans. Something which is external, we are not taking it into our system, but it's there. Noise is always there due to satellite, it's not always what rainfall we measure, it's not the rainfall that happened. So these are our three things which we feed. So if you remember our heat equation, or now what I'm trying to do is I'm wrapping your head around how these people make the use of this meshed earth, gridded earth, as well as this neural network, and made use of both of them, and then came up with this model. So if you notice the dynamical core, that seems gridded, right? So over there at every grid, some PDs are being solved. And physics tendency means change means differential. So that comes from machine learning. So you just find the change, how it was away from its prediction. So you integrate both of it in the ODA solver, which is the loss function, and then you get the output. Here, the learned precipitation is the part wherein you actually make the water balance equation. So you say that evaporation, precipitation, their sum should be 0 or sort of things. So you put it and expect it always. And you get an output. You iterate, you have epochs, and you get a model out of it. So this is the architecture of neural GCM, a demonstration of how PINN can help us. The cost of it is 10 times less than ECMFW, which is the state-of-the-art NWP model. very cheap. It is like 8 cents for a dollar. So it's good. And it's also very quick. You can also run the prediction on our laptop. So that's the power that it gives. And its accuracy is on par with the ECMFW. So these are the results. So here ECM, that's our Earth. We are trying to know what is the precipitation map at +2 days for different metrics, and probabilistic climatology. What is probabilistic climatology? Anybody understands by word what might it mean? So it is very simple. You have a grid, you have a place, you have a time, you will have a time series for it, for that grid. And you will just say statistically what is the likelihood, simple statistics. 2 mm say you will have rainfall more than 2 mm. So that's very simple baseline model. So that's a comparison way to compare our models. So we compared it and it came on par because it also respected physics. Traditionally, ML algorithms went haywire after 5 days. They were like not really making sense. Mars going negative and water going out of Earth. Things like that happened. But this enabled us to predict even till 15 days. 15 days is a big time for weather, hourly predictions. And also it enabled us to go for climatology stuff after 25 years and things. So that was what neural GCM is about. And those are the results. Yep. That's it. Okay, so do you guys have anything to ask? Any comments?
Can you go to the previous slide before the architecture of neural GCM? Before that.
Yes.
Not this one. Okay, there was slide where total loss was there, like lambda 1 plus
This?
loss data. Not there. After this slide.
What's your question anyway? You can ask.
Okay, I want to know what is the loss, the total loss equal to lambda 1 loss of data plus loss physics. So in the loss data, there was written like continuous rank probability score. So
Sorry.
continuous loss probability score.
Okay.
So what was that, and how it was different from the loss of physics? Like
you're saying L data was that?
Yeah.
That's up to us. You can take even in PI and MSc nobody uses. So you can define your own loss functions.
Okay.
I mean loss function, it's up to you. The L data. All the thing is you need to have some function about prediction and label. That's what it's saying, no? Yeah.
And in the architecture of neural GCM, we were introducing like this noise. So why we are doing noise?
So there are benefits about noise actually. Noise, first, it's intrinsically there. Whenever you observe something, there is noise. But you also add noise so that model is more robust. Because model should learn to ignore noise. So that's one reason we get noise into system.
Okay.
Yeah.
So the weather app in our phone uses this neural GCM, or it uses some other app to forecast the weather of next year?
So Google uses this because this is a Google product. This is ECMFW is the most popular one as of now also in operations, but its performance is par with it. And because it is cheaper now, ECMFW is also developing its own neural GCM, which it will make it up. Because ECMFW is free, like it's has a good reach. This was in December 2024. This paper came out. So it will slowly come into our mobiles also.
What's the full form of ACM?
It's some European medium weather range forecast.
Thanks.
Just a thought, like I've been working in projects using machine learning. So this thing is really new to me and it interested me. So you talked about neural GCM, an application of PINN. So is there any other application which we can use in some other domain? Like this is of climatology. So is there anything else which we can work on?
Yes. Many things. That's what I said. Any complex system you take, so for instance, you have some governing equation, all right. You are studying physics, let's say, and you have some governing equations, and so like we had the heat equations, del U by del X was 5 del square U by del T square. Now you want to find U as an expression of X and T. So you can do predictions ahead. So there you can use Pi and M to find U in terms of X and T, because once you have a model, essentially model is a mapping between input and output. So U is a function of X and T. That's the first application. Second application is when you just know that this system is governed by this del U by del X is equal to alpha times del square U by del T square. But for this particular system, you are unaware of the parameter alpha. If you are unaware of the parameter alpha, this will help you to get what is the alpha. That's second application. That's technically what it can help you solve. Now, in terms of real world applications, what do you work in? Like, what field are you in?
No, I was doing a project regarding a supply chain management data. So I was doing basically time series analysis. So I want to know, like, is there some application regarding it of this?
Not. I don't know particular supply chain. Are there some laws of supply chain or something? Do you study in theory?
Sorry, I didn't get your question.
Are there some laws or theory of supply chain that something is respected? See, the crux of it is something must be invariant. Something must be respected throughout. So if in theory you are learning that in supply chain this is being invariant, then that information of invariance you can embed it into the ML algorithm.
Okay.
So if you in your field go find in literature what is invariant, if you find it, embed it into the ML model.
Okay, that answers my question. Thank you.
Hi Aman, thanks for introducing beans. Actually, I came across a paper called as Universal Differential Equations, where they introduced universal differential equations. So basically, what they do is that they train the data using a neural net, and they use certain universal differential equation to model the, as you said, the inverse problem with the unknown alpha. So if we use, except for like, I don't know about the hydrological modeling parameters, but say instead of explicitly modeling evaporation and runoff rates, maybe we can use UDE's framework to.
We can use, pardon?
There is a universal differential estimator. There is another framework like, which is similar to Bean.
What's okay? That's fine, but like what?
So here I see that we in neural GSM we kind of take into account like different parameters. Like basically universal differential equation works with the unknown parameters also.
Yeah.
Like of a physical model, if we don't know various other parameters, if we know the known parameters, we train the neural network using that parameters and let the universal differential estimate.
So you're saying parameter discovery?
Yeah.
Yeah, that's the inverse problem, right? So I said it again last time also. So if you have that heat equation, del U by del X is alpha times del square U by del T square. That alpha is a parameter discovery that you have to do, right? So what will happen is very simple. When you will write the residual, in that alpha will be another parameter. You have a million parameter in the neural network. There will be 1 million plus 1 parameter, this alpha, and you will train on it. So you will discover this alpha also. So that's way to solve inverse problem. But there is one drawback which that's what not make it work is the moment the differential equations become a higher derivative, it becomes a problem because of vanishing gradients and the dimension. Once you increase 2D to 3D, the dimension increases folds. So that's why, but it has been much solved in the past 6 years. So you might want to find very specific niche models for your parameter discovery.
Yeah, I was just wondering because in this like climate modeling, like there are various like factors that we cannot have the physics equations for, right?
Yes.
So maybe that we can integrate it with the neural GCM and get some idea about those.
Yeah, that is physics discovery. That's one application of, yeah, we do that.
Makes sense. Thank you.
Anyway, whenever you are finding a function in a function space, that essentially is a discovery of how the input connects to output, right? So you can call it physics also, if that's, making interpretable. Again, please. Can you repeat? Little bit, come close.
Okay, so you told that physics informed neural network came in 2019 near to that. So can you give a glimpse that how much it is used in industry? So
This is
because
its use, yeah. In my field, this is the use, one popular use. In materials science, it's used very much because we know physics at micro level. Then we have sparse data in that there it's used.
which companies uses PINN?
NVIDIA uses. I attended one lecture where they have actually made entire framework of how to use PINN for the semiconductor stuff. See, it's a model. Model everybody can use for their own purpose. It's not something a company can take as a selling point that we use PINN. PINN is a model which will help you map a function, right? So Google also uses it. It's Google product. And material science, whatever companies work on that use it. Our IIT Gandhinagar research labs in that department uses it a lot. It's a popular thing. It's not like niche as of now.
So you mentioned about this adaptive learning.
No. It's just loss functions. Like you make lambda. You want to adjust so that lambda is that doesn't get biased. There are three components, right? That might be a different adaptive learning. I don't use that term. I'm saying you're trying to adapt to not make it very biased.
I can understand that, but what I mean to say is when you are putting those coefficients in your triplet loss, so how do you decide on it? By hit and trial run or?
It depends. It depends on the guy who's modeling. In this case, they actually just took few cases and they had it, like data they had. What is L data? What is L physics? And they found that this ratio is being consistent. So they took, I think, a factor of 100. If it is changing with time, then you can have a function mapping even for that. You can make it as complicated as you want, but empirically choose one number which makes it in the same range. That's up to you how intricately you want to model your system. But these guys did constant 10 or 100 something.
Okay, thank you.
Yeah, anybody, anything to ask, comment, discuss? All right. So we are done. Thank you. Thank you. So, did you get this collab file? Do you guys have laptops? I mean, this is second part. Yeah. We have till 12:30, no? So once everybody is on the collab file, you can just give a nod. We will start. This collab file was by Sarth. He is a computer science PhD at our lab. He made it. All right, shall we start? Okay. So, I mean, how many of you code, by the way? Okay. So I think you will understand it then. Yeah. So, there are a few examples in this hands-on tutorial. We will. My intent over here is to make you understand how a simple physics-informed neural network can be coded out. And so first we will start with some teaser examples. Pure data-driven, that is ML algorithms. The first cell, the cursor is following. So I won't explain you line by line. I will just explain you what the block does. So what we do over here is we create synthetic data X and Y, we map it with a neural network and we train it. Alright. If you don't follow on hands-on tutorial, you can ask. So we created this and we had this predictions, which is very bad. But now what we did is we said it that we made a loss function, which was, we knew the relationship between X and Y, which is of square. So we embedded it in the loss function and we saw that differential physics approach, it gets it. So that was just a teaser. We will go in detail in the next example. But just I want to say, if you embed a loss function, give it some info about X and Y, whatever you know, this is very simple. So it's so perfect, but we'll go ahead. This is just the intent is that you can embed some prior knowledge about X and Y and put it in the system and enable it to learn quickly. So anybody can interpret this. Do you understand what's going on? Yes. So what's the story? What is it saying? So you see the first one and you see the second one, okay? There is a difference, right? Yes, okay.
Will automatically like learn where should it go.
Yeah, in some sense, yes, you're right. Exactly. So that's the point. If you are training a machine learning algorithm, if you have data up till that point, so for the model, for the machine learning model, which has no prior knowledge about how those observations have been generated, it can go from any range to any range. It can go to a linear over here, over there. But the moment you say that the loss function should respect some kind of stuff, over here it is over this one, then even on this much data, it knew that it had to bend because the loss function informed it that please bend, kind of stuff. So that's the benefit, that when you go out of the range of your training data, the physics will enable you to keep it generalizable. So that's essentially the benefit. And it's very helpful in especially where systems characteristics are changing, like in our case, climate change. If climate is itself changing, then if you are modeling rainfall in our climate, it might not work in the future climate. So you might want something which is respected even in that climate, which is physics. So that's helpful. That's what PINN interests. So we will try to get into a little depth in this example. So you understood, no? Right? So this example will show you how it's actually coded out. Okay. So what is the answer for our question? Answer I'm already saying you. Answer is that first u of x is e raised to ax plus x. That's our answer that we want to know. Okay, that's the system's governing equation. That's the system's answer. Sorry, governing equation is du by dx is equal to a times e raised to ax plus 1. Or you differentiate it, you get d square u by dx square equal to a square e times e raised to ax, which you can substitute and take it back. So our net governing equation remains d square u by dx square minus a times du by dx is equal to a. You understand this? This is our governing equation. Our answer to what we are trying to understand is u as a function of x, different, okay? To know u and x are mingling, but we want it separate. So that's our answer. That's what is given. We will always know boundary conditions and initial conditions. That's also given. Now from here, can we go to towards our answer of separating u and x? So the plot for our thing is, it looks like this, just to gaze at it. And we define a simple MLP. You understand MLP? Simple neural network. If you don't understand, any part you can ask. Okay. So we are interested to calculate what? We are interested to calculate what is the physics residual over here? Anybody? Physics residual over here. What is physics residual? Who said? What? Exactly. So take A at that side. So you will put some U and X, right? You will get some residual. That is our physics laws. Yeah, but when we randomly initialize, there will be some residual, right? Because we are randomly doing it. So that is our loss, physics loss. So you get it, right? So that is our physics loss. To be able to code it out, you will have to, what you will have to do, you have X and T, in this case you have only X. So you go ahead, you get a U. Now you want to know what is du by dx, and you also want to know what is d square u by dx square. So for that, how will you do that? You use autodiff. So that's what modern frameworks, PyTorch, and it provides us. So you understand what deep learning is, right? Deep learning is essentially a function approximator. There is X, there is Y, there is some non-linear activation, but you can actually write down Y is equal to some blah 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 X, some blah 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 X square, and something you can write. So you will write U as a function of X, and then you will differentiate it. You will get du by dx. You will also get d square u. That's enabled by autodiff. That is the key innovation in PINN, by the way. So because now you are able to write the loss function, you can actually evaluate it at every iteration. So at this step, we do it. We find the du by dx, and we also find the d square u by dx square. And we put it into our loss function, as I said now. Boundary loss, just same as physics loss. And we train it, and we predict it. So that's it. Yeah, this is the very straightforward example of how you can find u as a function of x. Okay. Good time. Sir, where? So he works on deep learning with hydrological modeling. So he'll explain this part.
So this is one example in which you'll see how PINN can be done, used for the case of hydrology. Now we have so far discussed so many use cases of PINN. Another would be, which may sound absurd at first for a standard neural network. Can you train for a variable without having any ground truth signal? So just for a standard neural network, can you train for a target variable without having any ground truth signal for that? Okay, so this sounds absurd for the case of at least standard neural network, but you can do that for PINN. Let's take the example that you just have a standard patch of land. Let's take a noisy time series synthetically generated to represent rainfall and evaporation. Let's take a very simplified water balance over here. The equation you can see over here. I'll explain the nomenclature. The P represents the rainfall. The PET is your evaporation. This is the change in your soil moisture. Your soil will act like a sponge. It will also hold some water. It has memory. Yesterday's rainfall will change that. Then it works in persistent. It has a time flow. Then this Q is water flowing in a river. What goes out of the system. Okay. So entering the system, rainfall. Exiting the system, evaporation, and whatever is going out. This should equate to the difference in the soil moisture within the soil. Now, first of all, we need to synthetically create the data for this. We'll create all that. We'll just create a simple noisy sine waves for precipitation, evaporation. Okay. And these are some non-negativity constraints that we need to follow when we are creating the synthetic data, because we know, okay, rainfall cannot be negative. We know the soil moisture cannot be negative. Okay. Now we have our synthetic ground truth for whatever water is flowing in the river and whatever is the soil moisture content in the soil. Now the caveat is, in practical conditions, you can set up gauges to measure how much water is there in the river, but it is quite hard to get an estimate of the soil moisture content of any patch of land. The reason being, how many places you will sample. You will always end up with a sampling bias. Okay, so you cannot reliably estimate how much soil moisture there is. You would be end up with questions like, okay, till what depth I need to sample, how many sample points do I need, which places do I need to sample. Okay. The residual, as you can see over here, and you see we have this change in soil moisture, water going out of the system, and the difference between rainfall and evaporation. Okay, we set up our input X. The input is precipitation, evaporation, and time. So our input consists of a vector of precipitation, evaporation, and time. Our output will be, as you see, only water going out of the system in the river, Q. Okay. We have not used soil moisture anywhere in the ground truth label. There's only one. But when you see the architecture, you have two output neurons. Okay, but we only have ground truth label for one of them. We run it up, we train it as you would typically do. Just add a physics loss and let's visualize it. So this is just a random signal, but you see, you train it to exhaustion. And yeah, we expect that if we train it long enough, it will learn the signal, it will overfit the signal, it will mimic the signal, whatever you want to call it. And yes, it does mimic it. Okay, you have your ground truth Q, you have your predicted Q, completely matching, completely overlaid. But you see in the soil moisture, can you agree that visually, if I were to overlap these two figures, they would be completely overlapping? In this soil moisture, if I just move this blue line up to here, then will the blue and green completely overlap? Visually, you can see the similarities. Okay. Can anyone answer why there is this offset? So this will answer one of the things which people usually misunderstand about these physical constraints. If you blindly just put in constraint without understanding what that constraint is actually doing to the loss function, these kind of things can happen. So any guesses why there is this offset? Let me simplify. You have a neural network. Input is rainfall, evaporation, and time. Okay. Simple MLP. It's not an RNN, it's not an LSTM, just a simple rainfall, PET, and time. Output two neurons. One is Q, one is soil moisture. But we only have true value for Q. We see the predicted soil moisture against the true soil moisture, and we see a constant shift. It may be positive, it may be negative, but there's a constant shift. Why would that be the case? Any guesses? So look at the equation again. If you look it up, the constraint is applied on delta SM and not soil moisture itself. Similarly, the residual is applied on the change in soil moisture and not the soil moisture at time t. So when you are applying equation, you need to make sure what exactly is being constrained over here. So you have no control, you have no constraint and no prior information about what should be the value of soil moisture. But you know, if certain amount of rainfall happened with certain amount of evaporation, which resulted in some amount of water flowing out of the system, then the change in soil moisture, you know, by water balance. Not the exact value of soil moisture, but it is still a good indicator. In absence of any other, means imagine places which are so in need of this, but they lack the equipment to reliably measure soil moisture. Without having any ground truth label, they can at least estimate the trends in the soil moisture, when their soil is dry, when their soil is wet, because these things are indicator for agricultural drought, these things are indicator for many other practices as well. Okay. Then finally, you have a couple of examples for forward and inverse. Okay, you can run it up. Forward is just you have the governing equation, you would like to use the neural network to find out the simulation for it, so that you don't need to solve it numerically again and again, repeatedly, to save your compute. And inverse would be finding the parameter which best describes your simulation, whatever is given to you. So two such examples are given. So any questions out of these three examples that you have seen so far? I'm not sure why he entered into the audience. Okay, any questions so far about the PINNs? You can repeat the questions as well, that's okay, if you're still not clear. So, a couple of quick questions to see how much people understood. Does PINN mean only embedding the physics in the loss function? How many of you think that PINN means only embedding physics in the loss function? What if physics tells me which architecture to pick? I want invariance, I want symmetry, I end up picking graphs, I end up picking CNNs. Is that physics guided? Yes, okay. What if I use some known equations to create new features? Will that be physics informed? Okay. What if I use physics to evaluate which model is better? Mean squared error is not the metric to judge models usually. Means it's good to check model fit, but not model usability. My use metrics are specific to what industry is using them. So what if physics is informing the model evaluation? Then can that be physics guided? So this was the inception of it, but since then the field has evolved a lot. Physics use is not just limited to loss function. It also is used to enrich your features. It also guides the selection of architectures. It also guides the model evaluation as well. Okay? No questions, I see. You can run these notebooks. They are self-contained examples. We still have 10 minutes. If you have questions, you can say.
Yeah, we will close at 12:20. So if you want to run, you can run. If you want to ask anything, you can discuss. We'll leave at 12:20. Okay.